you. So let's get started. So welcome to my talk on developing microservices with aggregates. And really the goal of this talk is to show how some concepts from domain-driven design, specifically the aggregate concept, is actually a really good fit for developing business logic in a microservice architecture. And that's kind of strange in the sense that, you know, the book Domain-Driven Design by Eric Evans actually came out in 2003 which is sort of positively ancient. But it's remarkably relevant to designing today's applications. But before I get into that, a little bit about me. So I actually live in the San Francisco Bay Area. I got my start in the late 80s building Lisp systems, everything from garbage collectors all the way up the stack to IDEs. Eventually, of course, I programmed in Java. And back in 2006, so 10 years ago, my book Pojos in Action came out. That was all about Spring and Hibernate. And then 2007, I started tinkering with EC2, which back then was a very obscure service. I'm not even sure if the term cloud computing had been invented back then. Anyway, I ended up creating Cloud Foundry, the original version that was a PaaS for deploying Java applications on EC2. That got acquired by SpringSource shortly before SpringSource was acquired by VMware back in 2009. And I ended up spending 4.5 years in SpringSource, VMware, and then Pivotal. And then, I suppose, 3 years ago, I left, and since then, I've been doing everything related to microservices. So I do consulting and training with companies, helping them adopt microservice architecture. And I also have a startup called Eventuate that's building a platform to simplify the development of transactional business applications that use the microservice architecture. And encourage everyone to go check that out. There's a SaaS version and also an open source version of that product. And if you want to know more, go to this link, bit.ly, JAX 2016, learn more, and I'll send you links that are sort of to various chunks of information that are relevant to this talk. So here's the agenda. So kind of first, I'm going to talk about the problem with implementing business logic in a microservice architecture. Then I'm going to talk about the concept of aggregates as described in domain-driven design. And then I'm going to talk about how to use events to maintain consistency between aggregates and between services in a microservice architecture. And I'm going to finish up by talking briefly about an example application. And you'll be able to go to GitHub and see the code for that. So let's get going. So, the big idea behind the microservice architecture is that it tackles complexity through modularization. So in other words, when you use the microservice architecture, you functionally decompose your application into a set of services. So you're modularizing the application. We've sort of tried various different ways of modularizing it, packages, Maven modules, and so on. And in many ways, they've sort of kind of worked well, but once you get to a certain level of complexity, it tends to break down, and we end up developing large, complex, big balls of mud, basically. So the microservice architecture is another attempt to solve that problem by breaking your system up into a set of services. And each service corresponds to a business capability. So that's something your business does in order to deliver value to a customer or a shareholder. So that could be inventory management, account management, customer management, and so on. So if you think about an online store, it would end up with an architecture that looked like this. So for all the various sort of functions that a store has to provide, you would define a separate service. So a catalog service, review service, recommendation service, order service, and so on. Each one of those services has its own database. That's essential to ensure loose coupling between the services. But as you're going to see, that actually creates a whole set of problems that basically this talk is all about solving. Sitting in front of those services is an API gateway that acts as a facade that provides an entry point to the various clients of the system, whether they're web apps or mobile devices. And these can all be scaled independently, deployed independently, and so on. So that's kind of the microservice architecture. And really, we're relying on service boundaries to enforce modularity. Nice thing about service boundaries is that they're, a remoting API, they really encapsulate what's behind them. You can't cheat and access the implementation of a service, unlike sort of package system in Java, for example. So that's sort of a good way of enforcing module boundaries through sort of impermeable service boundaries. But there are problems. And basically, it's like you want to break things up, but the building blocks of our applications don't want to be broken up. So namely, if you look at a domain model is a tangled web of classes. So like an order has a reference to a customer. An order line item has a reference to a product. That's just sort of standard object-oriented design. The problem is when you want to put orders in the order service, products in a product service, customers in the customer service, so you want to split up your domain model, spread it across different microservices, you've got these object references that in theory would have to go between different services, and that just does not make sense, right? Because they're different JVMs, and you can't have object references between JVMs. So, our domain model, that's the standard way of building, implementing business logic in complex applications, is sort of at odds with how we want to decompose our application. Not only that, how we enforce invariants through the use of ACID transactions is also sort of at odds with the microservice model. So if you recall, each service has its own database. That's absolutely essential to ensure loose coupling. But then you look at just sort of regular sort of business logic and how that interacts with the database. So let's imagine that in order to place an order, you have to verify that that order will not exceed the customer's credit limit. You do that with a really simple transaction that selects from the customer, selects the existing orders, makes sure that there's available credit, and then inserts into those inserts a new order. And this will work really well, even if there are multiple simultaneous attempts to create orders for the same customer. The properties of ACID transactions will guarantee that a basic serializability and this business will be enforced. But then when we look at this from the perspective of a microservice architecture, orders are actually in one service, customers are in another. We can't write sort of database access code that just sort of works like that because it spans services. Not only that, this transaction, relying on a transaction, which, well, that would have to span multiple services as well, which would require some form of distributed transaction. The problem you have is that in modern applications, two-phase commit or distributed transactions are not an option. It's not a viable technology to use in modern applications. Because on the one hand, yeah, it guarantees consistency subject to a lot of fine print about how distributed transactions work with a particular database. But if you actually dig into two-phase commit, the coordinator is a single point of failure. It's a very chatty protocol. It might actually reduce throughput because data is locked for the duration of a transaction. It's also, from a very practical point of view, many modern technologies don't support two-phase commit. Most NoSQL databases, modern message brokers like Kafka don't support two-phase commit. So even if you wanted to use it, you can't. And not only that, there's also the CAP theorem that says that basically you have to choose between consistency and availability, and most people prefer availability. So you kind of have to give up on consistency. So that's a problem. So it's sort of like we want to break up our system, but our domain models don't decompose, and also our transactions don't decompose either. And also, we're also relying on NoSQL databases as well, which kind of have a very simplistic transaction model as well. So it's sort of a problem. Like, we want to decompose in order to sort of be modular, in order to develop fast and be agile. So we needed sort of a different way of designing our domain models and designing our transactions. And it turns out that the solution is in what I sort of jokingly refer to as this ancient text on domain-driven design. So that book came out in 2003, 2004, and it's sort of a very philosophically motivated approach to sort of using object-oriented design to build complex business logic. And in the book, there's a lot of sort of ideas in the book, but one of the sort of most kind of the ideas that people paid attention to a lot are the various building blocks for your domain models. So your entities, your value objects, your services, and your repositories. And those have pretty much been adopted by developers, and it's sort of part of everyday terminology. So if you look at JPA, it's got concepts of entities. If you look at like Spring Framework, Spring Data, for example, there's concepts of repositories, and services are, that's common terminology as well. But then there's another concept in domain-driven design, the concept of an aggregate. And that's actually been pretty much overlooked by developers, apart from those who are really into domain-driven design. I know that when I first read it, it was like, yeah, whatever. And I just sort of skipped over it. But it turns out that the idea of an aggregate is absolutely essential when you're building business logic in the microservice architecture. So an aggregate is a cluster of objects that can be treated as a unit. So it has a root. So in this example, we've got an order. You think about an order, the business concept of an order. Yeah, there's actually an order class, but there's more to an order than just that. You've got the line items, you have the delivery address, you'd also have payment information, and other sort of objects that collectively make up an order. And that actually turns out to be, in domain-driven design terms, an aggregate. So at some level, it's a really simple idea. It's a sort of a way of modularizing your domain model and sort of breaking it up into chunks. But what makes it particularly useful in the microservice architecture is that aggregates have to obey certain rules. So the first rule is that references between aggregates have to be in terms of the identity. So you don't have an object reference, but you basically have the primary key of in this case, say the customer. You have, instead of a customer object reference, you have the customer ID. Likewise, an order line item references a product ID and not the actual product. So, what's really interesting about this is that this sort of runs counter to the traditional object-oriented design sort of guidelines. If you go back and look at a classic book on object-oriented design, it says you should not have foreign keys in your domain model, right? That's sort of a design smell. But it turns out that this sort of restriction on how you design your aggregates is incredibly useful, because it means that your domain model is now a collection of aggregates that have very loose connections between them. And that's really good, because then when you want to break up your domain model and put your order in your order service, your customer in your customer service, and the product in the product service, the references between those aggregates are really just primary keys and not object references, which sort of solves this problem, because object references between services sort of don't have any meaning. So that works really, really well. Then the second rule that aggregates have to conform to is that a transaction can only create or update a single aggregate. And when I first read about this rule, it actually made absolutely no sense, because back then I was using a relational database. I could begin in a sort of monolithic architecture. I could begin a transaction, update whatever I want, commit the transaction. So this kind of rule that has sort of, from my perspective, strange philosophical motivations, just sort of didn't make sense, because of the technology I was using at the time. But it turns out that if you think about what this means in the context of a microservice, it actually accurately kind of captures the constraints that you need to live under in a microservice architecture. Namely, every transaction has to be contained within a single service. So if you think about a microservice as containing one or more aggregates, if a transaction can only create or update one of those, by definition, it's guaranteed to just reside within a single service. So, so we can update an order with one transaction. We can update a customer or update a product. So it exactly fits the constraints that we have to live under when we're writing business logic in a microservice architecture. Likewise, it exactly fits the constraints that you have to live under if you're using a NoSQL database as well, because they tend to not have a sort of arbitrary ACID transaction model as well. You can update a single MongoDB document, or you can update a single Cassandra row, and that's it. So if a document stores an aggregate or a row stores an aggregate, then this rule is a perfect fit there as well. So and I find this quite remarkable given sort of the age of this book and the philosophical motivations of this book as well. So this does mean that if there is something in your application that needs to be atomic, like there's two pieces of data that have to be updated atomically, then both of those things have to be part of the same aggregate. And later on, I'll talk about how to maintain consistency across aggregates, because most of the time, that's actually good enough. But if there is something that needs to be done atomically, it has to fit within a single aggregate. And because of that, you have to choose your aggregate boundaries fairly carefully. So before I sort of described how orders and customers and products were separate aggregates, but you actually have a choice. In theory, you could make orders and products and customers be a single aggregate. And I actually talked with some people who tried to do this once. They wanted just consistency in their application, so their application was one aggregate. It really did not work well. Among other things, updates to aggregates are done serially. So the fewer aggregates you have in your system, the fewer concurrent updates you can have. Also, if two users are editing the same aggregate, what the first user who saves will succeed. The second user who tries to save will be told, sorry, the data has changed underneath you, you have to start over. So, the more kind of clashes that the users encounter, the worse the user experience. So this is probably not going to work. An alternative approach which could work is to have for a customer and all of their orders to be the same aggregate. So you could imagine if you're using MongoDB, you just have one MongoDB document that contains the customer information and all of the order information, and then the individual products would be their own aggregates. And that would work, except in scenarios where there were concurrent attempts to update different orders for the same customer. You'd get sort of optimistic locking exceptions, which limit scalability, but it also could result in a poor user experience. So for those reasons, it's kind of best to have aggregates to be as fine-grained as possible, because that results in better scalability and a better user experience. But you really do have a choice when it comes to picking the size of your aggregates. So that's kind of aggregates in a nutshell. So they're just sort of ways of modularizing your domain model with very sort of weak links between those different modules, plus some rules around transactions that fit really, really well with the microservice architecture. So now I want to talk about kind of how to maintain consistency between aggregates, because sometimes, or quite often, you have business transactions that need to maintain data consistency across multiple aggregates. A classic example would be transferring money between two bank accounts. Each one of those is a different aggregate. And given that we have this rule where one transaction updates one aggregate, we need a sort of different way of enforcing data consistency. So here's the example that I like to use a lot these days. So you have orders. Orders belong to a customer. Customers have a credit limit. And there's a business rule, of course, that the open orders for a customer cannot exceed the customer's credit limit. So that means, of course, that when you want to create a new order, you have to, before doing that, you have to verify that that order will not exceed the customer's credit limit. And you have to do that in a way that will deal with multiple simultaneous attempts to create orders for the same customer. Earlier, I showed how you can easily do that with an ACID transaction, but in this system, because they're different aggregates in different services, we need a different mechanism to ensure data consistency in this scenario. And the sort of the standard approach to this is to use an event-driven architecture. And the way that works is really quite simple. The big idea is that when one service changes its data, it publishes an event which gets consumed by one or more other services, which can then change their data, update their aggregates, to be more precise, in response to make the system consistent. And it might involve multiple steps. But in the case of order processing, it's quite simple. So a request for an order comes in. The order service actually creates an order, but it creates it in a pending state, sort of kind of in a state that indicates that it needs to have its credit limit checked. And it publishes an event saying the order is created. That gets consumed by the customer service that performs the credit check, actually reserves credit for that order. And if it's successful, it publishes an event to say the credit has been reserved. And if it's unsuccessful, it publishes an event to say that the credit check has failed. The order service then consumes that event and updates, either approves or rejects the order. So we're sort of we're achieving the same thing as an ACID transaction that does the credit check and creates the order. But in this case, it's a series of 3 local transactions, one in the order service, one in the customer service, and one back in the order service again. And there's actually another word for this is saga. It's sort of an alternative to a long-running distributed transaction, a sequence of steps where each step is triggered. Each step publishes an event that triggers the next step in the sequence. It's sort of reminiscent of a workflow. Here's another way of looking at the same thing, slightly different view, right? So a request comes in, the order is created, an event is published, the event is consumed, the credit is reserved, an event is published indicating that it gets consumed, and then the state of the order transitions to approved. So it's this sort of multi-step workflow. And that's sort of the standard way of maintaining consistency across, in this case, across multiple aggregates, but in general across multiple services, across multiple databases, without using distributed transactions. I first read about sort of an approach like this many years ago in a paper by an architect at eBay, which was describing how, even though they were using SQL databases, they didn't want to use distributed transactions for the reasons I outlined earlier. So this works pretty well. But there are it's a more complex programming model. In particular, if you think about an ACID transaction, it can update whatever it wants. And then if it finds at some point that a business rule has been violated, it can just sort of roll back the transaction, and it would be as if nothing had ever happened, right? But with this model, where you've got a sequence of local transactions, rollback is now much more complicated. You effectively have to roll forward by explicitly executing new transactions that undo the changes you have done previously. So in the last example, in a sense, if the credit check failed, we're basically rolling back the creation of the order by canceling the order. Another interesting scenario is where you're transferring money between two accounts, where you have debited the from account, and then when you try and credit the to account, you find that the to account has been closed, at which point you need to then recredit the from account. And of course, an interesting scenario arises when you discover that the from account has subsequently been closed, right? And then you've got this sort of money left in limbo, and at which point you have to apply some other business rules in order to handle that. So there's all kinds of interesting scenarios, and you have to think carefully about how to implement these compensating transactions. But in general, it's not too challenging. But there's also an interesting technical problem with implementing this approach. Namely, in order for it to be reliable, you have to atomically update the database and publish a message. In fact, in essence, you need that needs to be done as a transaction. And it's kind of equivalent to needing a distributed transaction that involves the order database, in this case, and the message data and the message broker. Because if you only did one of those things, so for example, you inserted an order, and then before actually publishing the event, you crashed, that would leave the system in an inconsistent state, right? There's this order sitting there that will never have its credit check, or never have the credit reserved. So those two things have to happen atomically. But remember, also ironically, the standard way of doing that would be to use a distributed transaction, involving involving your JDBC database and JMS. But remember, two-phase commit is not an option for the reasons I described earlier. So we need a different way of atomically doing the update of the database and publishing the event. There's actually a few different options for that. And I'm not going to sort of go into them in any detail, except for one. But for example, you could, one approach, which seems a little out there, but actually has been in use in LinkedIn, is to actually tail the database transaction log or commit log. So you're basically leveraging, for example, the MySQL master-slave replication by observing changes to the database and publishing them to a message broker. And so that technique like that is actually in use at LinkedIn. And then you could do things similar with database triggers and so on. But the technique that I want to talk about here is one known as event sourcing, because that's sort of kind of a technique that has actually sort of evolved within the domain-driven design community. And it's sort of a really appealing way of sort of implementing your business logic and persistence in an event-centric way that works really, really well within the microservice architecture. So the big idea with event sourcing is, well, there's just events. You're not actually, as you're going to see, the way you store your aggregates is as a series of events. So there isn't a separate notion of updating the database and then publishing an event. There's really just one thing, saving an event in an event store, which is actually equivalent to publishing it. So the way it works is as follows. So for each aggregate, you identify the domain events, which are usually state-changing events, but they can also represent attempts to violate business rules. And for each one of them, you define event classes. So you're actually treating events as first-class citizens in your domain model. And there's actually a technique called event storming, which is sort of a workshop format where you get domain experts in the room and ask them, what events occur in your domain? And then from there, from the events, you actually work backwards to identifying your aggregates and so on. Absolutely fascinating. But regardless of how you come up with the events, like for an order, you would have like order created or canceled or shipped, approved, rejected, and so on. And then you would define classes corresponding to those. So that in itself is interesting, but where event sourcing is really quite unique is how you actually store your domain objects in the database. So the standard way of persisting a domain object is really just to map it to a row in a table. That's our standard Hibernate JPA approach. So for an order, it would be a row in an order table. With event sourcing, you don't do that. Instead, you actually store the events themselves in the database. So you actually would have, for instance, have a table called events that has the event ID and event data and the entity ID and so on. So it would look something like this. So when an order is created, you insert an order created event row into that table. And then when it's approved, you insert another row into the table, another event. And then when it's shipped, you're going to insert another row. And this is how you store, in this case, orders in your database as a series of events. Likewise for customers and all of the other entities. So kind of conceptually, in your system, there is simply one table in your database, the events table. In practice, there would be other ones as well. Like on the previous slide, there was an entities table as well. But there is no longer an order table, a customer table, or a product table. So it's a very different way of storing, sort of persisting your domain objects. And then when you need the current state, like you want to, equivalent to how, say, JPA queries the database, and then from the data it gets back, reconstructs a domain object in memory, the way that works in an event source system is that you load the events and then replay them on the domain object to reconstruct the current state. An order class is sort of somewhat simple, but if you think about a bank account, that would be represented in the database as a series of debits and credits, and you could reconstruct the current balance by loading those debits and credits and summing them up, right, with the initial balance. And in a functional sense, if you're into functional programming, that's actually doing a fold over the event stream in order to reconstruct the current state, a fold or a reduce. So the way your system would then look, given this event-centric approach, is that the order service is storing orders as a stream of events in the event store. The customer service is storing customers as streams of events. And then they're also subscribing to one another's events. So the customer service knows about orders, and the order events and vice versa. So that's the model. And then if you look at how requests are handled in this system, like a request comes in to update an order, first thing you're going to do is load the order's events from the event store. You then instantiate a new order object using its default constructor. You then replay the events by applying them to the order. You process the command, which represents the request. Like in this case, it would be reserve credit. That gives you new events, which you then apply by calling apply again. And then you save those new events in the event store, which would insert them into the event table. And that would actually be done with optimistic locking so that you could handle the scenario where there are simultaneous attempts to handle, to update the same order. So other services can then subscribe to events, so the customer service could subscribe to the order events, and then when they occur, it gets notified. It can then update the customer, so perform a credit check, for example, or whatever it needs to do based on that event, which would then, of course, trigger new events to get published, which could then trigger something else to happen in some other service. And then other services can also subscribe and do arbitrary things. A service might update a materialized view. There's a related pattern that I don't have time to talk about today, known as CQRS, where you're maintaining denormalized representations of the data for querying. So one simple example of that is, imagine that you need to do text searching, right? That's just sort of a really common pattern. In this architecture, that would be a CQRS view using Elasticsearch, which would get updated in response to this stream of events. Those events could also be used to send out notifications as well. Text messages, mobile alerts, send messages to remote systems to tell them to perform some action. Completely arbitrary. So the event store itself, that is basically a database in the sense that it has an API for inserting events by primary key, retrieving events by primary key. And it also is like a message broker because it has a way of subscribing as well. And there's a variety of solutions for doing that. People have built their own. There's also dedicated event stores, like in .NET. There's Get Event Store, Lagom, if I pronounced that correct, Lagom, which is Swedish for just right, and you have to pronounce it just right. Is another one, and then my company has built one as well. It's sort of open source and SaaS. So there's sort of a bunch of benefits to using event sourcing. So the reason we got into this, right? It solves the data consistency problems in a microservice architecture. It's a good way of implementing an event-driven approach. Works very well with aggregates. It also is great because it generates a stream of events. Whenever your data changes, you have an event by definition, and that can be used to feed into machine learning algorithms, send out notifications to users, arbitrary things. It also eliminates the OR mapping problem. Even though we have JPA, it's not a perfect solution. There's just this inherent mismatch between the object world and the relational world. Well, with event sourcing, you're only ever persisting events, which have quite a simple schema in general. So you basically have eliminated the problem. Another really nice feature about event sourcing is because every state change has a corresponding event. By definition, that means that you have an audit log that is guaranteed to be accurate. The event can contain the identity of the user who performed that change, right? And every change gets written into the event store. And that's really nice, because if you think about the standard way of implementing audit logging, that's usually just kind of added on as an afterthought, and there's no guarantee that it's actually consistent with the business logic. So with this mechanism, it is, by definition. So that's quite good. Another benefit of this is that the entire history of every domain object is preserved. So you have the ability to perform temporal queries. You can ask questions like, what was the state of this bank account 2 weeks ago? And you would answer that question by finding the events that have occurred since the beginning of time up until 2 weeks ago and replaying them to reconstruct the current state, which is really powerful. That's useful in domains that require auditing, when sort of financial regulators come knocking at your door and asking about trades that occurred sometime in the past, for example. So it's not a silver bullet. There definitely are drawbacks, right? So it's sort of a different style of writing your business logic. So adopting it means changing your business logic, though it's a very mechanical, I've gone through this, it's a very mechanical transformation. There's also a learning curve to think in terms of events, but it's usually not too difficult. Another challenge is that events, once they've been written to the database, they don't go away, which is good because it means you've got this permanent record of everything that has happened. The downside is that events, the schema of them tends to evolve over time. And so you're going to need a mechanism for sort of, when you load events, you're going to get back potentially a mixture of old events like version 1, version 2, version 3 events, and you're going to have to put in place a mechanism to sort of deal with that in some way. The nice thing is usually the events don't change too much, and you can change them in backwards compatible ways, like you add extra attributes and you just have to default values. But there's some issues that you have to be mindful of. Another challenge is that this is a message-driven system. Message brokers give you at least once delivery guarantees, right? Which means that you could get the same event multiple times, and so you have to potentially deal with getting the same event multiple times. So you end up having to, hopefully your event handlers will be idempotent, so they don't mind being invoked multiple times, or you're going to have to write event handlers that keep track of the events that they have seen and discard repeats. Usually that's not too difficult, especially if your events have an ID that is always increasing. You just have to keep track of the high watermark and discard events that are not later than it. So that's not too bad. Hold that thought. Another issue you have to deal with is that querying the event store is challenging. So for instance, trivial query would be like find accounts whose balance is greater than X. Normally, normal schema, there is a column that has the balance, so it's just a simple select statement. When you're using an event store, there's no explicit representation of the current state. So that would mean that a simple query like this would actually have to use a nested select that would fold the events together. And that would get complicated real fast and possibly inefficient as well. So you end up having to use command query responsibility segregation, which I mentioned earlier, and maintain these denormalized representations of the data that you can then query. But for a bunch of reasons, you often have to do that in a microservice architecture anyway, because you need to do joins across multiple services, but you can't do that using SQL because the data is private to each service. And so CQRS is just a natural pattern to have anyway, regardless of whether you're using event sourcing or not. So that's kind of event sourcing in a nutshell. I just want to quickly show some code. So yeah, here's the example application, which you probably can't read. So it's comprised of multiple services. So there's the customer service that has the customer aggregate. There's the order service that has the order aggregate. And then there's the order history service that's actually maintaining kind of one of these denormalized views of the data using MongoDB. So we've got 3 microservices. And there's actually a use of Kafka in here as sort of a back channel from the customer service to the order service to say, hey, you just created an order for a customer that doesn't exist. But that's sort of a minor thing. So, they're all connected to the event store. So you can find this diagram in the code in GitHub. So if we look at the customer service, right, it's handling a post to create a customer, and it's got a customer controller, customer service, customer aggregate, and some event handlers for the order events. Here's the customer. So it's got some, the credit limit, credit reservations, and then the event sourcing-based business logic consists of sets of process methods that take these commands to perform an action, and they return the list of events that represent the state change. And then there's the apply methods that take an event and actually perform the state change. So we've actually taken our business logic methods like reserve credit that figure out how to update the state and then update the state, and split them explicitly into 2 methods. One of them figures out how to update the state and returns events. And then the second one is an apply method that actually takes the event that was generated by process and then does the apply. And as you'd expect, right, we need to generate events because they're saved in the event store, and we need a mechanism to apply the events in order to reconstruct an object when we load it from the event store. So here's the actual code, which I have no idea whether you can read at the back. But there's some process methods. And the one that's interesting is the process method for reserve credit, which is saying if the available credit is greater than or equal to the order total, right, there's enough credit, then return a customer credit reserved event, otherwise return a customer credit limit exceeded event. So that's sort of our business logic for reserving credit. Nothing, that's... And then the apply methods are really simple because they're representing what has already happened. And so they have no conditional logic, and they're just simply updating the state in response to the event. So in the case of customer credit reserved event, it's just simply putting an entry into the hash map saying that this order has reserved this much credit. So that's that. Here's the controller. It's just invoking the create customer service. So that's sort of no surprise. It's written in a slightly different style because it's sort of reactive using Java 8 completable futures. But that's the detail. Here's the customer service method for creating a customer. And all it's doing is calling save, passing in the command to execute on an aggregate repository. And what save does, it creates a customer aggregate, processes the command, applies the events to the customer to actually update it, and then saves those events in the event store. So it's a convenience method that implements the boilerplate for creating a new aggregate. And then here's an event handler for the order created event. And all that's doing is updating a specified customer, updating a customer with this ID, telling it to process the reserve credit command. So it's just finding the aggregate in the database, loading it, processing the reserve credit command, and then actually saving those events back into the event store. And there's an error handler for the case where that customer ID was not found, which actually then publishes a message using Kafka which is sort of a back channel back to the order service to say, hey, you told me to reserve credit for this customer, but this customer doesn't exist. Which is just, I mean, there's a whole bunch of interesting little details there that I don't have time to go into. But you can find this code on GitHub. So that's just one of the standard eventuate examples. So that's pretty much my talk. So sort of in summary, right, aggregates are the building blocks of business logic for microservices. You want to use events to maintain consistency between aggregates, and event sourcing is a good way to actually implement an event-driven architecture. So that's my talk. Thank you for listening, and love to talk more. So find me on Twitter, send me email, and also if you want to know more, just go to that JAX 2016 Learn More link. So thank you. Hope you found it useful.